So, good afternoon, everyone. So this is our first undergraduate math colloquium this year, and our topic is special values of the Riemann zeta function. And my name is Trevor Liu, and I'm currently a year 3 mathematics student. And our topic today is on the special values of the Riemann zeta function. And in our talk, we'll talk about first the Bessel form. The pi square over 6 thing that most of you might have heard about, like the 1 plus 1 over 4 plus 1 over 9, that 1 over n squared thing. We will talk about how Euler obtained pi square over 6, how Euler solved it. And then we generalize, we want to study the values of the Riemann zeta function at even integers. And if time permits, we can talk about something about zeta 3. We don't know a formula for zeta 3, but we know it's irrational. If time permits, we can talk about that as well. So let's talk about Euler's solution. So in 1734, Leonard Euler, he said that if we sum over all the reciprocals of the perfect squares, we get pi squared over 6. So that's what Euler said. And I'm going to present his proof. And later on, I will also talk about how to generalize this to study the sum of the 4th power, 6th power, or any even powers. And we can get a formula for it. And then these numbers, these are rational numbers, and we know that B0 is 1, and we can compute all other numbers by a recursive formula. So that eventually we can solve this problem completely. And that will be the main topic of our talk. So let's begin with Euler. So we will talk about Euler's solution, but we need to know that during Euler's time, limit, continuity, analysis, they're not a thing yet. We just follow by intuitions. And it turns out that many of Euler's intuitions are correct. So we first present Euler's intuition, and then we need to justify why his intuitions are right. So that's why we have 2 sections. So first one is the solution, then we do a rigorous proof. And so this is Euler, and this is Weierstrass. You might have heard Weierstrass's name for his non-differentiable function. Like he presented a function that is continuous everywhere, but differentiable nowhere. So Weierstrass is a guy who wants rigor in mathematics. So he wants to make things rigorous. So Euler presented his solution of Bessel problem, and it was not until Weierstrass that this whole thing gets rigorous. So let's first look at Euler. So to solve the Bessel problem, Euler defined 2 quantities. The first one is just the sine function, the harmless trigonometric function we have. And the second function is a product. And if we look at the 2 functions together, if you want, you can just plot the function using decimals. And when we include terms in this product, the 2 functions that get closer and closer. And Euler is claiming that, well, yes, when n goes to infinity, the second function should converge to the first function. And for the second function, we know that this is a polynomial. And if you know something called the Vieta's formula, we can actually expand the polynomial and find some formula for the coefficient of x squared. Suppose that we have this polynomial, we want to find the coefficient of x squared. By combinatorics, this can only happen when we multiply an x squared term in one bracket with all other ones. So this means that the coefficient for x squared must be this sum. So we have 1 over pi squared, we have 1 over 2 squared pi squared, and we add them up. And that gives us the coefficient of x squared in the expansion of this polynomial. And because we believe that this Fn converges to F, it is reasonable to infer that the coefficient of x squared should converge to the coefficient of x squared in this f of x. So if we compute the coefficient of fx squared of f of x, then we finish Euler's proof. And since this is sine, And we know from calculus that this has a Taylor expansion at x equals to 0. And we know the coefficients well. So we can just make the deduction. We know that if we do the Taylor expansion, then sine of x is going to be x minus x to the third power over 6. If we divide by x on both sides, we see that the coefficient for x squared is exactly negative 1 over 6. And if we look at the formula before, we know that it's also zeta 2, it's also minus zeta 2 over pi squared. So if we put these two equations together, we get the conclusion that zeta 2 is pi squared over 6. And most part of Euler's proof are actually rigorous, except the third thing. We don't know whether this product converges to f of x or not. We don't know whether this is true or not. And now I'm going to give like a brief justification of the reason. So, yes, Euler believed that the infinite product converges to sine. And yeah, let me show you that formula again. So this is Euler's identity. He wants to prove that the product, if this thing goes to infinity, it should converge to sine. The first observation we have is that the zeros still match. Like the zeros of the right-hand side, if n goes to infinity, the zeros coincide. So this means that if we cancel out all the zeros, we get a function that is essentially non-zero. And our next step is to show that the ratio becomes a constant. And that is what we are going to do. So this is mainly based on Weierstrass's work. So Weierstrass, in order to formalize this, he developed a general theory so that it studies what kind of function can be represented by some infinite product. And each term is going to account for a zero. So Weierstrass developed the theory of complex analysis and then made a general conclusion. And we are going to use this general conclusion to do something about sine. So if we look at this, the statement of the theorem, if the function is going to have some zeros, and if the reciprocal of the reciprocal square of the zeros, if we sum them up, if they converge, then we should have a product representation. And then this g is just another function. The reason that we can put this on an exponential is because it's non-zero. So as long as we take a logarithm and the term inside does not go to 0, we don't have a problem. So that's why we put a function on the exponential. And this is known as Weierstrass's factorization theorem. Now we are going to use this factorization theorem to make some conclusions on the sine function. So if we accept this theorem, we can check that the zeros of sine function comes with this. Because we have divided the term by z, we know that the function is non-zero at the origin. So we can say that the zeros are just pi, minus pi, 2 pi, minus 2 pi. And if we sum over the squares, sum over the reciprocals of the squares, we end up doing like a summation of 1 over 1 square pi squared plus 1 over 1 square pi squares plus 1 over 2 square pi squares all the way. Because we know that the sum over 1 over n squared is convergent. That's the p-series test. Because we know that this converges, we can use Weierstrass's theorem to say that, okay, we can represent sine as an infinite product. So the first term is accounting for the positive zeros, and the second term is for the negative zeros.
Yes. Shall we explain to people what's p-series test to them? Maybe they have no idea. You guys have any idea about what's p-series?
Analysis 1.
Sorry?
Have you talked about series convergence?
Yeah.
So there's a thing called p-series.
No, but we're going to.
No problem, no problem.
Next lecture.
It will be beneficial if you learn them earlier. Never mind, but just the fact that we need here is that this series is going to converge. And then we can use our theorem and do all the things.
The whole idea is the infinite summation of like 1 over n to rp.
Yes,
right?
yes, and in that case, p is greater than 1, then we are.
If you guys know what we're talking about. Okay, cool. Sure?
We'll publish the slides afterwards, and in case you have any questions, just email me. No problem. So this series converge, and we don't need to worry about we can just use the theorem to get an infinite product representation. Once the series converge, we have two products. the first product is going to account for the positive zeros, the zeros on the right-hand side of the plane. And the second product is for the zeros on the left-hand side of the plane. And we see that there's like an exponential terms. But if we just match, say, 1 with -1, 2 with -2, then these exponential terms, they get cancelled. And we can also merge these two terms together to get a difference of squares. So we see that all we need is just to determine the ratio. Like our final task is to prove that this e to the g is exactly 1. If we did that, then we finish the proof. So now we have the infinite product. And we also see that the function is going to be the infinite product multiplied by an exponential of some other function. Since if we expand all the details, this will be like a lecture in complex analysis. I'm going to summarize. So analysis is the art of playing with inequalities. So in analysis 1, you will eventually talk about using inequalities to make conclusions about limits or the convergence of series. And now we're going to use some inequalities to eventually show that this e to the g of z is going to be 1. First, by taking limits, so sine of z over z. If we take the limit as z goes to 0, we know that it's 1. And for h, we also know that z goes to 0 is an infinite product of 1. So h of 0 is also 1. As a result, we know that e to the g, this function is going to be 1 at z equals to 0. As a result, we can take g0 equals to 0. And moreover, by some technical computations, we can show that the ratio f divided by h is going to be less than exponential function of the absolute value of z raised to the power of 1.01 when z goes to infinity. The reason I use 1.01 is just this exponential has to be greater than 1 to account for some terms. So as a result, we can bound the real part of g by z raised to the power of 1.01. And there's this thing from complex analysis that shows you that if you have a function that is well behaved on the complex plane, and its real part satisfies some bound, then this function can only be a polynomial. And this is Borel-Carrathiel-Dory theorem. So, any questions? That's all right.
What's this theorem coming from? It kind of just seems to be.
So it's a theorem that comes from the development of the expressing a function as an infinite product. Because you know a certain bound for the exponential of a function, then the exponential of an absolute value is exactly the absolute value of an exponential is the exponential of the real part in the exponent. So that's why we begin with a bound for the real part and then make a conclusion about the function itself. That's the origin of this kind of theorem. And once we have this theorem, we can conclude that this g of z is a polynomial of degree at most the flow part, the integer part of the exponent. And since if we take the flow function of 1.01, it's 1. So g of z must be a constant multiple of z. So it's a polynomial of degree at most 1. So, and we also know that g0 is 0, so this means that g can only be a constant multiple of z. And because we also know that this h of z is an even function, and sine of z over z is also an even function. So the quotient is going to be an even function again. But we say that that even function is e to the az. So a must be 0 to make this an even function. So eventually we conclude that this g must be identically 0, and we conclude the proof that the sine of x over x is exactly the infinite product. For those curious about like how to develop a general theory of infinite products, you can find some complex analysis books, and they usually talk about this. So now we finish up the proof of Euler's Bessel problem. We can start discussing the general formula, like how to express how to find an expression for zeta function at even integers. And before actually talking about zeta function, we need to make a digression to talk about sum of positive powers, because that explains the origin of the numbers here. Like we see that there's a number b here. Before talking about zeta function, we need to talk about where these numbers come from, and these are known as the Bernoulli numbers. And we first talk about some Bernoulli numbers. And before Bernoulli numbers, we have this question. So if p equals to 1, we know that this formula, so this is just the sum of the first few powers. If p is equal to 1, we know that it's, if p is equal to 0, we are summing ones, so it's n. If p is equal to 1, this is just a familiar formula for arithmetic progression, just n times n plus 1 over 2. And for sum of squares, we can eventually prove another formula, that is a cubic. And now we want to derive a general formula for any integer power p. And these are due to the works of two mathematicians. This is Johann Faulhaber, and this is Jacob Bernoulli. I think Bernoulli is more famous. So Johann Faulhaber, he derived formulas when p is less than or equal to 17, like he somehow gets 17 polynomials and work them out. And Bernoulli is going to generalize this for any integers. And the way to do that is to introduce a new kind of numbers called the Bernoulli number. So eventually we have this gigantic formula. But the point is that these are just some constants, and this is a power. So we know that this is a polynomial. And because Faulhaber was the first person who worked on this, this is called Faulhaber's formula, but not Bernoulli's formula, although it's Bernoulli numbers inside. And now we are going to prove this formula. We're going to use some tricks to prove the formula. And it will be convenient if we work out the generating function. And we are going to work out the generating function and then compare the coefficients and then conclude. So if you do generating function, we introduce a summation. And the quantity we are looking for also involves a summation. So now we have a double summation. And in number theory, it is usually great if we have two summations, because when you interchange the order of summation, you get something interesting. And it is the case here. So we have an infinite sum, and we also have a finite sum inside. So let me actually just write out a few steps. So we know that this SPN is the sum of powers. So this is originally a summation inside the infinite sum. And I'm going to put this k to the p power with x to the p power. So they become together. And then I move the finite sum outside. You can justify this because everything converges absolutely. So now we have the series inside. And if we look at the term, this is some power over some factorial. And that gives you exponential function. So you have an exponential function inside now. But this one is a geometric progression, so you also have a formula to sum over. So that's the generating function you have. And we want to make a decomposition. So this generating function becomes a product of these two quantities. And the first two quantities, the first quantity, you can just use the Taylor expansion for the exponential function to get a formula for the coefficients. And the second one requires Bernoulli number. And eventually, you are going to do something called a Cauchy product to put the pieces together. So I'm going to define. So if we look at the second function and we make the substitution that y equals to minus x, it's going to give you Bernoulli number. Then that's how you define the Bernoulli number. Just the coefficients. And roughly speaking, we are going to put the coefficient together. So the first thing is that we know that the exponential function is just 1 plus the summation of k greater than or equal to 1, z to the k power over k factorial. This means that e to the n of x minus 1 is just k equals k greater than or equal to 0, k plus 1 factorial, and then inside we have n to the k plus 1 power times x to the k plus 1 power. And if we divide x, this k plus 1 just becomes k. So that explains for the first term in the summation. And for the second term, because we have y equals to minus x, we put a minus 1 power here. So that's just the first two terms. Now this is a power series, and if we gather the like terms, we get something called the Cauchy product. And after manipulating the coefficients, you will eventually arrive at this. So that's like the result of Cauchy product and comparing coefficients. And eventually, when you put this p to the p factorial to the right-hand side, it's going to give you this expression. We have a p factorial over n factorial times p plus 1 minus n factorial. If this p factorial becomes a p plus 1, this becomes a binomial coefficient. And that's why you have this in the end. So that finishes the proof of Paul-Haber's formula. But another question is, well, we have just turned this unknown quantity into a formula that contains more unknown quantities because we don't know how to compute this Bn. Although we know that it's a coefficient of the generating function, but taking derivatives of these kind of complicated generating function is not that efficient. So before turning to the next topic, we need to first know how to compute Bernoulli numbers. So the first thing we can notice is that if we take the reciprocal of the generating function, and we know the coefficients of this function very well because we can just use the Taylor expansion for the exponential. If we multiply them together, we get 1. So this means that if we can use Cauchy product to express the product, the coefficient of the product of these two series, then we can just compare the coefficients so that the constant coefficient is 1 and the other coefficients are 0. And this is precisely what we are doing here. So this is the first expression we have. And after Cauchy product and some simplification, we get this identity. So this just means that this bound of summation is going to give you 1 when p is equal to 0, and it's going to be 0 when p is greater than 0. And when p is equal to 0, this summation only involves one term. It only involves b0. So from this identity, we can immediately know that we know that the first Bernoulli number b0 is just equal to 1. And for other numbers, we can use this identity to get a recursive formula. The idea is that we isolate the last term. We isolate bp. So the summation only has terms from 0 to p minus 1. And we can turn this into a recursive formula so that the next Bernoulli number is just given by the summation of the other ones. And if we do some computation, we know b0 is 1, and we know b1 is negative 1/2. We know b2 is 1 over 6. We know b3 is 0. b4 is minus 1 over 30. And the computation of b2 and b4 are important because they help us evaluate the zeta values. So having finished our discussion of Bernoulli numbers, we can start talking about Riemann zeta function at even integers. And the idea is that we have, so in Euler's proof, we use an identity for sine. We express sine function as an infinite product. And then we compare the coefficients to get zeta 2. And for other even integers, we still need to start with an identity and then compare coefficients. But now the identity will be cotangent. So in this section, we are going to derive two expressions for the cotangent and then compare coefficients. And the conclusion is that the first expression involves a zeta power, involves zeta values. And the second function it kind of resembles the generating function for Bernoulli numbers. And it is this identity that allows us to conclude. And for your convenience, I'm going to write down the generating function for the Bernoulli numbers. So now we are going to derive the first expansion. So this is the identity we kind of proved in the previous section, the product formula for sine. And to obtain cotangent, we know from the chain rule that the cotangent is just the derivative of logarithm of sine. So we are going to take logarithm on both sides of this quantity. If we take logarithm of a product, it becomes a sum of logs. That's because just log of a times b is just log of a plus log of b. And this is just a natural log. So log of sine of x is just log of x plus the logarithm of this bunch of terms. And if we differentiate on both sides, the left-hand side becomes cotangent. It's cosine x over sine of x. The right-hand side becomes 1 over x. And this is just a consequence of applying the chain rule. And it becomes a sum over some rational functions. And yes, so after some simplification, we see that the cotangent is expressed in this manner. And for the term that is inside, I'm writing this in this manner because it resembles the geometric series. Like we know that when z, the absolute value of z is less than 1, 1 over 1 minus z is going to give you a convenient expression. That's just 1 plus z squared all the way. And I'm going to use that to turn this into a double summation, and then interchange the summation, and we get something interesting. That's the general idea. So this is cotangent, and I'm going to expand the term inside into the series. And I'm going to plug the series into the series, so we have two summations again. And now we're going to interchange the order of summation. So that if we interchange, if we move the k summation outside, we have x to the 2k minus 1, and then we have pi to the 2k outside. And the terms related to n is exactly the summation. We see that this is just the summation of 1 over n to the 2k, and we're summing over n. And this just gives you the zeta function as 2k. So this finishes the proof of the first identity we have. So that finishes the proof of the first identity. And now we are going to do the second. For the second one, it's also Euler. So Euler is famous for quite a number of formulas, and the first one I was impressed about is the one about complex explanation. So that's the formula that is usually presented to audience, and the actual formula is e to the ix is cosine of x plus I times sine of x. And if we use this formula, we can re-express the cosines and the sines using complex explanations. And now, once we have this expression, we can express cotangent as the ratio of these two quantities. So because cosine is on the numerator, we have plus on the numerator and minus on the denominator. Because we divide sine by I, we multiply this expression by I. So that's the Euler's formula. And to simplify, we multiply both sides. We multiply numerator and denominator by e to the ix. So we get a plus 1 on numerator, minus 1 on denominator. And this expression contains contains explanations on numerator and denominator. And we are going to eliminate one of them. We eliminate the one on the numerator. So we replace this plus 1 with minus 1 and plus 2. So these two terms, they get cancelled. So we can get a 1 outside of this term. So it's I plus another term. So this is cotangent, and this is also, and so we move this here. And because we know that the generating function of Bernoulli numbers looks like that. So we just want to organize the terms so that we get the Bernoulli numbers out. As a result, we replace this 2i with 2ix, and then the yx outside. So this becomes a generating function for the Bernoulli polynomials, Bernoulli numbers, and we just plug in the expansion. So that expresses cotangent using Bernoulli numbers. So this is what we have now. So that's the first expression of cotangent using zeta function. And now we have the second expansion using Bernoulli numbers. So if we plug in m equals to 2k here, we should get something like b of 2k over 2k factorial times 2i raised to the power of 2k times x to the 2k minus 1. So this term is going to agree with the term for zeta. As a result, we have minus 2 times zeta of 2k over pi to the 2k equal to this Bernoulli function expression. We know that I squared is equal to 1, so I to the 2k is just minus 1 to the k. And then 2 to the 2k is just itself. So that's our first expansion. And now we are going to isolate zeta, the zeta function. So zeta of 2k is just these bunch of things. And because we know that we can use the recursive formula to compute all the Bernoulli numbers, we can essentially evaluate all of the zeta values at even integers. And I suppose we can take a break.
Shall we?
You can pause this.
Okay.